Bismillahirrahmanirrahim. Welcome to the 10th lecture of Mechanics of Solids. Today we are going to proceed with our discussion of the torsion that was initiated in the previous lecture. Today we are going to advance our concepts of torsion by studying angle of twist, statically indeterminate torque loaded members, then the torque in the solid non-circular shafts, and thin walled tubes having closed cross sections. So, for determining the angle of twist, the first question arises that why do we need this angle of twist? Occasionally, the design of a shaft depends on restricting the amount of rotation or twist that may occur when the shaft is subjected to a torque. Furthermore, being able to compute the angle of twist for a shaft is important when analyzing the reactions on statically indeterminate shafts. For example, oil wells are commonly drilled to depths exceeding 1,000 meters. As a result, the total angle of twist of a string of drill pipe can be substantial and must be determined. Now we are going to develop a formula for determining the angle of twist of one end of a shaft with respect to its other end. The shaft is assumed to have a circular cross section that can gradually vary along its length. Also, this material is assumed to be homogeneous and to behave in a linear elastic manner when the torque is applied. We will neglect the localized deformations that occur at points of application of the torques and where the cross section changes abruptly. By St. Venant's principle, these effects occur within small regions of the shaft's length and generally they have only a slight effect on the final result. So now, using the method of sections, we have taken a differential disk of thickness dx, which is located at a distance of x from the beginning. The internal resultant torque at this location is Tx because we are assuming that the torque is varying along the length of this shaft. Due to Tx, the disk will twist such that the relative rotation of one of its faces with respect to the other is d phi. You can see here that due to this twist, let's say if this was the initial position of the face, then due to the twist, this position will get displaced by an amount d phi. As a result, an element of material located at an arbitrary radius rho will undergo a shear strain gamma. Like this change in angle will cause a shear strain, or obviously, like, shear strain is the change in angle by the original angle, so this will result in this shear strain of gamma. The value of gamma and the d phi are related by this equation, as I discussed this thing in the previous lecture, that how this d phi and gamma are related to each other. Okay, now since gamma is equal to tau by g, and we have this tau is equal to tx into rho by jx, then we can have gamma equal to this thing by just replacing tau in this equation. And thus if we replace gamma, this value of gamma in this equation, and take the integral of this differential for the whole length, we come up with this expression. In this expression, phi is the angle of twist at one end of the shaft with respect to the other end, and it is measured in radians. The internal torque at the arbitrary position x found from the method of sections, and the equation of moment equilibrium applied about the shaft's axis. The shaft's polar moment of inertia, Jx, is the shaft's polar moment of inertia expressed as function of position x, and G is the shear modulus of elasticity of the material. Usually in engineering practice, the material is homogeneous so that this G is constant. Also, the shaft's cross-sectional area and the external torque are constant along the length of the shaft. If this is the case, then the previous expression for the angle of twist can be expressed in this form, in which we are replacing T of x with T and J of x with J. The similarities between this equation and that for the axially loaded bar that we developed in one of the previous lecture can be noted. A crucial point to remember here is that this equation, this equation for the angle of twist is often used to determine the shear modulus of elasticity of a material. To do so, a specimen of known length and diameter is placed in a torsion testing machine like this one. The applied torque and the angle of twist are then measured along the length L, and then from this, by replacing the angle of twist and length in this equation by the known values, we determine the shear modulus of any kind of material. Now, if the shaft is subjected to several different torques, or the cross-sectional area or shear modulus changes abruptly from one region of the shaft to the next, the equation that was derived in the previous slide can be applied to each segment of the shaft where these quantities are all constant. Then the angle of twist of one end of the shaft with respect to the other end is then found from the vector addition of the angles of twist of each segment. This is the equation for this case. Now, in order to apply this equation, we must develop a sign convention for both the internal torque and the angle of twist of one end of the shaft with respect to the other end. To do this, we will use a right hand rule, whereby both the torque and the angle of twist will be positive, provided the thumb is directed outward from the shaft when the fingers curl to give the tendency for rotation. So this is our first example. In this example, we are having gears that are attached to a fixed end steel shaft, and these are then subjected to torques. If the shear modulus of elasticity is 80 gigapascal and the shaft has a diameter of 14 mm, we have to determine the displacement of this tooth P on gear A. The shaft turns freely within the bearing at B. So first we have to determine the internal torques that are acting at different points on the shaft before we can determine this the displacement of the tooth P. By inspection, the torques in segments AC, CD and DE are different because different torques are being applied at the endpoints here. So if we draw a free body diagram of this shaft, we'll know that in the segment AC, the torque is 150 Newton meter clockwise. In just to the right of this segment C, the torque is, or in the segment you can say in the segment CD, the torque is 130 Newton meter, or it will be minus 130 Newton meter actually, because it is anti-clockwise. And similarly in the segment DE, here DE, the torque at this location will be the sum of the torque of 150 minus 280 minus 40, and it will be actually minus 170 Newton meter. So now based on these torques, we will use the equation derived in the previous section to determine the angle of twist of this end A with respect to the end E. So the polar moment of inertia for the shaft is this. We have determined this simply from the diameter given, and then applying that equation for each segment and then adding the results algebraically, we have algebraically means that we have to give due consideration to the sign convention. So for the torque, we have 150 Newton meter, the torques that we have determined from the free body diagram for each of the segments, their corresponding lengths, and J and G are constant for each of the segments, and thus we have determined that the rotation of end A with respect to end E is this minus 2.12 radians. This answer is negative, and it means by the right hand rule the thumb is directed toward the end E of the shaft, and therefore gear A will rotate as shown here in this towards the right, or toward it will have a clockwise rotation. The displacement of tooth P on gear A can be determined by multiplying this angle with the diameter, with the radius of the shaft, and thus the displacement of tooth P will be 21.2 millimeters. Sometimes a torsionally loaded shaft may be classified as a statically indeterminate shaft if the moment equation of equilibrium is not sufficient to determine the unknown torques acting on the shaft. For example, you can see here that this shaft is fixed, supported on both the ends, and if we take a section of this shaft at any location, then we'll have and apply this moment of the summation of moment in the direction x is equal to 0. We come up with this equation T minus TA minus TB is equal to 0. But now here we are having only one equation and we have two unknowns. So this equation is not sufficient to determine the unknown torques acting on this shaft. So whenever we encounter this problem where the equations of equilibrium are not sufficient to give us the unknowns, we have to incorporate, or we have to consider some additional equations, which are usually called the compatibility equations. These equations are derived by the requirements of fulfilling the kinematic conditions. So in this case, the kinematic condition is that the rotation of end A with respect to the end B should be equal to 0. Thus, this is the kinematic condition. And now if we from the previous equation that we have derived, if we substitute this phi A by B by the required torque formulas, we come up with this equation, and now we have two equations and two unknowns, and we can easily determine the unknown torques in this shaft. Second example, in this we are having a solid shaft that has a diameter of 20 millimeter. It is subjected to two torques, one of 800 Newton meter and the other of 500 Newton meter. We have to determine the reactions at the fixed supports A and B. If we draw this free body diagram of this equation, we'll come to know that this problem is statically indeterminate, since there is only one available equation of equilibrium and there are two unknowns. Thus we require that minus TB plus 800 minus 500 minus TA should be equal to 0. Determine the unknown torques by using the condition of compatibility, which requires that the rotation of one end of the shaft with respect to the other end should be equal to 0. This condition can be satisfied by partitioning the shaft in different segments. So if we take three segments of the shaft before the location where the torque TA is applied, we can express the angle of twist in terms of the torque TB only. So for the first shaft, it will be minus TB divided by JG. Then we'll have plus 800 in the other segment. The applied torque, or the internal torque, will be equal to 800 minus TB. Thus, it for the second segment, the angle of twist will be determined using this equation or this term, and for the third segment of the shaft, we'll have this particular term for determining the angle of twist, and thus this equation has only one unknown, that is TP, and it can be solved simply for this one unknown TB here. And then using the equation 1, we can have determined the torque TA at the other end of the shaft. The negative sign indicates that TA acts in the opposite direction of that which was originally shown in the figure, and thus in this way, using the compatibility condition, we can solve the indeterminate torsion problems. Okay, so now we have reached to the third section of our lecture today, in which we are going to consider solid non-circular shafts. It was demonstrated in the previous lecture that when a torque is applied to a shaft having a circular cross-section, that is one that is axisymmetric, the shear strains vary linearly from zero at its center to a maximum at its outer surface. Furthermore, due to the uniformity of the shear strains at all points on the same radius, the cross-sections do not deform, but rather remain plane after the shaft has twisted. Shafts that have a non-circular cross-section are not axisymmetric, so their cross-sections will bulge or warp when the shaft is twisted. If we take a look here at the grid lines, we can notice that the grid lines deform on a shaft having a square cross-section when the shaft is twisted. Not only there is deformation in the longitudinal lines, but the lines that are along the cross-section are also getting deformed. As a consequence of this deformation, the torsional analysis of non-circular shafts is really complicated, and we're not going to actually consider this in this text. However, we are going to consider a simplified form or a simplified way of determining shear stresses in the non-circular shafts. Basically, using theory of elasticity, it is possible to determine the shear stress distribution within a shaft of square cross-section. Example of this shear stress can be seen here, of this shear stress variation on a circular the square cross section can be seen here. Because the shear stress distributions vary in a complex manner, the shear strains they create will warp the cross section, like in this way. This cross section is, you can see here, is not square anymore after the action of torsion. The cross section has changed, so this cannot be dealt with simple linear elasticity principles. In particular, it can be noticed that the corner points of the shaft must be subjected to zero shear stress and therefore zero shear strain. The reason for this can be shown by considering an element of material located at one of these points. Here you can see, here we are just considering the material located at this point. One would expect the top face of this element to be subjected to a shear stress in order to aid in resisting the applied torque. This, however, cannot occur since the complementary shear stresses tau and tau dash acting on the outer surface of the shaft must be zero. Without going into the details of the derivation using theory of elasticity, for this particular course, we are just going to consider the final result for these cross sections. We can see here in this table the tau maximum and the angle of twist for the different cross sections. In all these cases, the maximum shear stress occurs at a point on the edge of the cross section that is closest to the center axis of the shaft. Uh, in this table, these points are indicated as dots on the cross section. Okay, one point to remember, one critical or crucial point to remember from the discussion is that shafts having a circular cross section are the most efficient because they are subjected to both a smaller maximum shear stress and a smaller angle of twist than a corresponding shaft having a non-circular cross section and subjected to the same torque. Okay, so now we are on our third example. Here we have an aluminium shaft that has a cross-sectional area in the shape of an equilateral triangle. We have to determine the largest torque that can be applied to the end of the shaft if the allowable shear stress is 8 ksi and the twist angle at its end is restricted. How much we also need to determine that how much torque can be applied to this shaft if a circular cross section is made from the same amount of material. So by inspection we know that the resultant internal torque at any cross section along the shaft's axis is also T. So using the formula for the tau max and phi from the previous table, we come up with this thing that the allowable should actually be equal to the maximum torque that occurs on this cross section. So now here the torque comes out as T is equal to 1350 poundage. Actually, the allowable stress should be equal to the maximum shear stress that can occur on this cross section, and the allowable this allowable angle of twist should be equal to the maximum angle of twist that can occur in this particular cross section. Thus, the maximum torque that can be applied based on this allowable angle comes out as 170 pound-inch. By comparison, we can notice this thing: the torque is limited due to the angle of twist. Like, due to this angle of twist, very small amount of torque can actually be applied to this shaft. If we want to determine the um, allowable torque for the circle having the same material as the aluminium, the area of that circular shaft should be equal to the area of this triangular shaft. Thus, from this equation, we have determined the radius for that shaft, or the diameter for that shaft actually, and then the limitations of stress and angle of twist then require that, again, the allowable shear stress is based on the material, and from the equations for the maximum shear stress that can occur on a shaft with circular cross section, we have determined the value for the torque, and similarly for the angle of twist. Again, here the angle of twist is the limiting provides us with the limiting torque, but we can see here the limiting torque for the circular cross section is greater than the one that can be applied with the shaft having triangular cross section. Now we are going to discuss thin wall tubes having cross sections. Thin wall tubes of non-circular cross sections are often used to construct lightweight frameworks such as those used in aircrafts. In some applications, they may be subjected to a torsional loading. In this section, we will analyze the effects of applying a torque to a thin walled tube having a closed cross section, that is, tube that does not have any breaks or slits along its length. Such a tube having constant yet arbitrary cross sectional shape and variable thickness, like this one, as shown in this figure, are commonly used. Since the walls are thin, we will obtain the average shear stress by assuming that this stress is uniformly distributed along the thickness of the tube at any given point. Before we do this, however, we have to discuss some preliminary concepts regarding the action of shear stress over the cross section. Okay, so now we are considering a small element of the tube having a finite length S and differential width dx. At one end, the element has a thickness Ta and the other end it is Tb. Due to the internal torque T, shear stress is developed on the front face of the element. Specifically at end A, the shear stress is tau A, and end B it is tau B. These stresses can be related by noting that equivalent shear stresses tau A and tau B must also act on the longitudinal sides of the element. Since these sides have a constant width dx, the forces acting on them are dFA is equal to tau A into TA into dx, and dFB is equal to dFB is equal to tau B into TB into dx. Equilibrium requires these forces to be of equal magnitude and direction, so that we'll come up with this equation: tau A into TA will be equal to tau B into TB. This important result states that the product of average shear stress times the thickness of the tube is the same at each point on the tube's cross-sectional area. This product is called shear flow, and it is generally expressed in these terms, that tau average into the thickness will be equal along the cross section of this tube. Since Q is a constant over the cross section, the largest average shear stress must occur when the tube's thickness is the smallest. Now, if a differential element of thickness T, length ds, and width dx is located in this tube, it is seen that the front face over which the average shear stress occurs is dA is equal to TDS. Hence, dF is equal to tau average into this area TDS, and this equals as QDS, where Q is equal to FDS and dF by ds. In other words, the shear flow measures the force per unit length along the tube's cross-sectional area. It is important to realize that the shear stress components shown in this figure are the only ones acting on the tube. Components acting in the other direction, like in this figure, cannot exist. Actually, this is because the top and bottom faces of the element are at the inner and outer walls of the tube, and these boundaries must be free of stress. Instead, as noted above, the applied torques cause the shear flow and the average stress to be always directed as tangent to the wall of the tube, such that it contributes to the resultant internal torque T. The average shear stress can be related to the torque by considering the torque produced by this shear stress about a selected point O within the tube's boundary. The shear stress develops a force dF is equal to tau average into dA on an element of the tube. This force acts tangent to the center line of the tube's wall, and if the moment arm is h, the torque is dt is equal to h into df. For the entire cross section, we have to take a line integral actually for this boundary. Here the line integral indicates that the integration must be performed around the entire boundary of the area. Since the shear flow Q is equal to tau average into T is constant, it can be factored out of the integral so that T is equal to tau average into T. A graphical simplification can be made for evaluating the integral by noting that the mean area shown by the blue colored triangle in this figure is actually this AM is equal to 1 by 2 into H into ds. Thus, if we replace this H into ds by this dam into 2 average t, and then this integral can be replaced by this mean area. Solving for the tau average, we have t divided by 2 into thickness into the mean area. Here tau average is the average shear stress acting over a particular thickness of the tube. T is the resultant internal torque at the cross section. T is the thickness of the tube where tau average is to be determined. AM is the mean area enclosed within the boundary of the center line of the tube's thickness. Since Q is equal to tau average into T, then the shear flow can be throughout the cross section becomes as this thing. So now in this final example, we have to determine the average shear stress in a thin-walled tube having a circular cross-section of mean radius and thickness T, which is subjected to a torque T. Finally, we have to determine the relative angle of twist if the tube has a length L. The mean area for the tube is AM is equal to pi Rm square. Rm is the mean torque we are taking, mean radius that we are taking for this cross-section. And applying the equation that we have just derived in the previous slide, we come up as tau average is equal to T divided by 2 into pi T into Rm square. Now we can check the validity of this result by applying the torsion formula. For this, we have to determine the J. For this J, we have this R naught 4 minus Ri I4 R raised to the power 4, and thus we come up with this equation for this modulus. Now, since Rm is approximately equal to R naught, which is approximately equal to Ri, and the thickness can be approximated as R, or thickness is actually equal to R naught minus Ri, we come up with this equation for J, and by substituting that in the normal equation for the shear stress, we have come up with this result, which agrees with our original approximation. The average shear stress distribution acting throughout the body's cross-section is shown in this figure. Also shown is the shear stress distribution acting on a radial line as calculated using the torsion formula. We can notice here that the tau average acts in a direction such that it contributes to the resultant torque at the section. As the tube's thickness decreases, the shear stress throughout the tube becomes more uniform. And then we can apply this equation for determining the angle of twist. The integral represents the length around the center line boundary, which is actually 2 pi rm. So by substituting this integral with this 2 pi rm, the angle of twist comes out with this equation. And so now this marks the end of our lecture. Thank you very much for listening. If you have any questions, you can post those in the comments.